The Energy Game Changers 2020 is moving on to its final presentation. As we have spoken about industry, we've spoken about society, we looked at the question of sustainability. What is more than to look for the future? Before that, just a quick reminder that we're using the WorkSup solution. So if you're currently watching us via WorkSup, you can network with other people by creating a small profile and then starting conversations with other participants of this conference. So on the down right side of your screen, you should find that option. Also, we're using questions from you to deliver to the presenters today. So for the final presenter as well, you can ask questions through the Q&A opportunity in the WorkSup solution. So if you're currently not using WorkSup, then you can find the link to the WorkSup event that this conference is using under the SMAGRINET Facebook page. So coming back to this conference here and now, how to solve the challenges related to the large-scale integration of renewable electricity generation and high-voltage direct current grids. We bring to you the last presentation of the day, a view of the future by Sadiq Basha, who is currently the professor within the Grenoble University in charge of electric engineering, power electronics, mathematics, and control lectures for various undergraduate courses. His main research interests are modeling, control, and simulation of energy systems, and also supergrids and microgrids. He has supervised countless of theses, wrote a book, and wrote and published several of hundreds of pieces on this topic. Currently, he is Program Scientific Director within the Supergrid Institute in Lyon. So on the topic of high voltage direct current as a mean for large-scale renewable energy integration.
Do you hearing me?
Yes, now we can hear you.
Thank you. Thank you. Thank you very much for this nice invitation. It's a very interesting conference, workshop. And thank you again for giving me the chance to explain my favorite topic of research, I mean renewable integration. First, I think I can launch the slides. Okay. Is it possible to launch them? Do you see them?
Yes.
No? You see them? Okay. I'm currently Program Scientific Director, of course, of the program Architectures. And architectures means the planning and the operation of these new grids, which are coming now by the necessity of renewable integration. Not only renewable integration, of course, but many other issues I can explain here. I start my presentation by just a very rapid site about renewables, pointing on the main issues. After that, we will discuss if the grid is prepared or not for these challenges or locks, and we can finally discuss how HVDC systems can provide solutions for these problems. At the end, some discussions maybe. I'm ready for that, of course. First of all, you know, I think we can discuss days and days about renewables, the benefits of renewables, the drawbacks, and so on and so on. But I'd like just to say that it's very, very well-known issues now because it's largely shared between researchers, the large public, of course, newspapers, and so on. Then I can see you have many drivers. The first driver is, of course, we have to think about our children. This is the sustainable development. Voluntarism sometimes, kingly decisions, of course, and some ideologies. And there is some ideologies against renewables as well, of course. The climate change, environmental issues, and so on and so on. Very well-known issues. But I'd like just to point on 3 or 4 main problems. The first is the huge and unexpected growth of these renewables. This is in this picture you can see from the Worldwide Energy Association that we reached for 2019. We have not, of course, the data from 2020, but the data for 2019, we reached 650 gigawatts of installed power, cumulative installed power. It doesn't mean that all these systems are producing today. Some of them are, I think, stopped. Other are not, are decommissioned, and so on and so on. But 650 gigawatt means the equivalent of 650 nuclear units. It's, just to give you a very interesting sight about that. This is for, especially for wind. The second is photovoltaics. Photovoltaics is really a revolution. 5 years ago, nobody expected this huge growth. It's due mainly to, of course, the decrease of prices, the market which is open now, and the competitivity of these systems. You can see a huge growth. This is the first challenge, the first problem, how to host this huge amount of energy. The second point, the variability. In this picture, you can see you have a variability in the day, minutes after minutes, and you can have variability between seasons, between months, and so on and so on. It means that, of course, there is a natural aggregation sometimes. If you are looking at the scale of a country, the variability is a little bit smoothed, but it remains. The second problem, of course, variability. Another problem, how to drive, to transfer, to transport these huge amounts of power. Huge, huge, huge. From the north to south, we can see you have hydro in the center of Europe here. You can see the center. The south, in North Africa, solar energy, wind with the Atlantic facade from the north, from I think Norway up to Morocco, Senegal, and so on. We have some other systems. We can provide flexibility as PSPs, but pumping storage plants can be, I think, assimilated to hydro electricity, but as a storage system. And we can also speak about the distributed storage, which is can contribute to smooth or to give flexibility, provide flexibility as electric vehicles, but it's another conference. First, then, the problem for these huge, I think, highways, we have bottlenecks, of course. They are limiting capacity today. We cannot drive more than it could be possible. I mean, for instance, it's not possible, for instance, today to transfer which is planned in terms of solar energy in North Africa to Europe. And we are limited capacity as well to transfer the huge capacity of hydropower plants in Norway to the UCT grid. I mean the grid, the main grid in the mainland grid in Europe. Third problem. The fourth problem. You know, we have the law. Physical laws are not. It's not possible to change them. You can change the regulation. You can change, I think, some grid codes. You can change everything, but Ohm laws are not, or Kirchhoff laws cannot be changed. It's physical. Then, if you want to sell or to send a given amount of energy from Portugal to, for instance, Germany, what are the paths? It's very incredible. This is a simulation made with a common book we produced with Professor Krapp from Belgium. A very nice guy, very important person, a respectable person, who wrote, we wrote together this book showing what could be the problems. One of them is this one. We haven't said from Portugal, the energy, an amount of 100 to Germany, the ways are very strange. In the picture above, in the left-hand side, you can see if I can transport, we have just 31%, which is transferred from France directly to Germany, even if 100% from France from Portugal to France, of course, for Spain, this is the same grid. It means that you have additive losses. You have no mastering this energy flow. You can see another picture. Okay, my internet connection is unstable. Okay, if you have some issues, please tell me. The second in the picture above, right-hand side, this is another point from France to Belgium. You know, Belgium and France are neighbors. Normally, it will be directly sent. No, it's not the case. A part is going to Germany, coming back from Netherlands to Belgium. Another part from Switzerland to Austria, another part to Italy, and so on and so on. Then there is necessity to masterize, to control these flows. Another challenge. Okay, but the most, I think, terrifying problem, I'm a little bit, it's like a warnings. Big warning is the loss of inertia. What does it mean? The inertia of the actual grid is provided by the huge synchronous machines, which are, I think, the source of the electricity energy. And these machines are mechanical. Then they have an inertia. The inertia is a kinetic energy stored inside. It's a huge storage system. But by using power electronics interfaces with renewables, this inertia disappears. By disappearing, you can see in the picture what is the consequence. The first consequence is the rate of change of frequency is increasing, and the nadir as well. The nadir as well of frequency, or the dip of frequency, and then this problem, this issue, can lead to load shedding, or sometimes load shedding is brown out, or a blackout. As you know, a blackout today, one blackout in UCT means a loss of 1 day GDP for whole Europe, Central Europe, or the main European community. Then we are pointing another problem. You can see renewable energy integration is not straightforward. We expect a lot of problems. And how can we do? Okay, we can solve anything by a huge storage system, but it's not competitive. You can imagine mountains of batteries, or dams where PSPs everywhere, even in the desert, but you cannot imagine that. Then we have to, I think, collaborating many solutions. But all these solutions are related to the grid. Then question, is the actual grid prepared? I don't think so. You can see the actual grid is separated into the transmission and the distribution one. The transmission one is the hugest one, well equipped with remote control, with breakers, with everything, masterized, monitored, and so on. But the distribution system is the poor parent of the grid. And this poor parent is hosting as well a lot of renewables. And we expect now new problems with electric vehicle fleets, of course. Then we have to adapt this system. How to adapt? We will discuss that. Then we have to face huge energy flows, uncontrolled quantities, uncontrolled paths, lots of inertia, and many disturbances. Then I can start from a dream. This dream is well known as Desert Tech Project. Desert Tech Project, the aim of this Desert Project is to make the Sahara, back to desert, as a huge source, huge host for renewable sources, mainly thermal solar plants, and hydroelectric and wind energy along the Atlantic coasts. But this problem, first problem we have to face, how to send this energy to Europe. We can go through the Mediterranean Sea, but the Mediterranean Sea is very deep. I don't see if you can see here the mouse. The direct path from north to the south to the north through the Mediterranean Sea means that we have to cross or to send cables in very deep sea, more than 400 4,000 meters, but it's not possible due to mechanical constraints. You cannot immerse more than today 100 meters of huge cables because the mechanic tension make it cut itself. It's not possible to use them. Then we have two solutions: going through Italy or going through Spain. Another problem. These two grids are bottlenecks because there are not enough investment. It's an AC grid, classical one, and there is no enough capacities to send this energy through these grids. Another problem. Okay, there is a solution. This is what is called the Mediterranean ring via two huge grids, and the Algerian one and Egypt's one. The Egyptian grid and the Algerian grid are the most powerful grids in Africa. It's like two giants. They decided, the two TSOs and transmission system operators from both sides decided to, we have to connect ourselves and try to collaborate. It was a pre-catastrophe because all these two giants are fighting one against one, and you can see what happened, the inter-area oscillations of power, which lead automatically to instability. Then they opened a possibility. You have no other possibilities, just to think about new grids. What could be the solution? Ex nihilo solution. Ex nihilo solution is to build a new grid, destroying the first one, building a new one. Okay, it will cost, I think, more than, this is approximative data, 400 times of world GDP. World GDP. Then, conclusion, it's not possible. Okay. Second solution, let the market leading us. Okay, if we can pay, if we have to have a payment, back payment, investments, private investment, and so on, maybe. It's not the solution at all, because electricity is like human rights. You know, without electricity, there is no education. Without electricity, you have no health system. Everything now is depending. There are no communication, no internet, and so on and so on. Then it's like in French, we say c'est un droit. It's a right for everybody. Then it's too serious. You cannot give all the words to the capital or to the market. What could we do? Okay, can we do? But we have just to deal with the old grid. We cannot change it. We have to address new requirements, these problems I discussed, and the cost, of course, may be acceptable. If we have not, if the capex and opex are too high, I think we can give up with renewables. We have then two options. One is to increase the HVDC, high alternative current, high voltage alternative current transmission grid today by adding new lines or some other devices, or adding a new framework beside this one, which is HVDC grid. Two solutions are digged by from the seventh. This is a program. There's a conclusion of a contract within the seven framework program of the European Union, which is ERN 40. ERN 40, they propose two possibilities. One of them is to propose to increase the AC system by new lines, high voltage lines, and adding some flexible AC transmission system, which are power electronic systems. And sometimes, which is necessary, when you have two no synchronized grids, you have to connect them by HVDC in green in the picture. Second solution, what is the possibility? The possibility is to mesh an HVDC grid beside or over this old grid with new lines, grid line. And you can see here, you can increase, you can have like a highways for energy in Spain and Italy to solve these problems of capacity. Okay. I check how much time. Okay, I have time. Okay. What is the HVDC? What are the differences? In a very, very simple way. I think It's very approximative, but it's just a picture in order to point on the differences and the advantage of one regarding another one. First, to transmit the energy, you have a limit. It's the impedance with AC. This formula here is related to any transmission system by neglecting the resistor here regarding the reactance. Reactance is very important regarding the resistance. Then we can make this approximate formula, which explains that the maximum of the power which can be transmitted is the product between the two both sides voltage divided by reactance. This is the maximum. And it can be modulated by the difference between angles between the two voltages. For DC, there is no reactance. Okay, reactance is a very large one. It's just limited by the resistance. What I can say here, you can conclude by a very approximative way, but very, I think it's a very sensitive case. By the same quantity of iron pylons, insulators, the same insulators, the same quantity, the same quantity of copper, you can transmit 3 times energy than the AC classical lines. Then this is a solution to increase largely, hugely, the transmission capacities with HVDC. The second, how to control the flows. Of course, for HVDC in both sides, you have converters, power electronics converters. And then you can control the flows in terms of direction, but as well in terms of quantity. Okay, then we solved the problem of choosing the good path to transfer the energy. Third problem, okay, problem of stability. Of course, by adding some converters here, you can play on the impedances, what is called the virtual impedances. By virtual impedances, it's like I think it's like a series facts, and you can dump some oscillations of frequency, of orbital angle differences, and so on and so on. It means that it could be a good way to solve some problems. But we have other solutions. One of them is to integrate. We'll discuss that after some storage elements inside the huge converters, which are called multimodular converters. It's like very high buildings full of submodules and so on and so on. Okay. Another point, this is wind farm, offshore wind farms. You can as well decrease the number of conversion levels. Then you can increase the global efficiency. You can control as well. You can make some what is called the grid forming operation. And then you can stabilize more and more the grid. Okay, another mean to improve this integration. Okay, but it's not, I think, it's not very happy story for everyone, but for everyone and for everything. But we have just to make to integrate some issues related to HVDCs. Then we have new concerns, especially for the collaboration, the cooperation, or the interaction between the AC grid and the DC grid must be kept with caution. Second problem is really a big problem is the protections. Protections, why? Physical protections and algorithmic protections. Algorithmic protection is the calculation to decide what switch I have to open. Physically, it's a problem with breakers. The AC breakers are very simple compared to the DC breakers. AC breakers, you have the alternating current. One time it crosses zero. When crossing the zero, the plasma is turned off. But with DC, you have this zero cross party. Then you have to add additional components, and now research are more focused on hybrid DC breakers, integrating power electronics and mechanical breakers. and surge arresters, and limit current, fault limit current limiters. Protections. Okay. It's like ESOP tongue. It furnish solutions and it furnish problems as well in the same package. But question, technology. The technology are off the shelf. I mean, available and mature. What are the technologies? First, power electronics. Power electronics, the DC lines, I think, are very old, but the first lines were based on thyristor technologies, which is more LCC, line commutated current commutated converters. This solution is very robust, it necessitates a lot of filters, and the reversibility of needs to reverse the voltage. Then it's not possible to mesh a grid with the solution based on thyristors. To mesh a grid, we need to have the same, roughly the same voltage everywhere. But if you want to reverse, you can just reverse the currents. But with LCC, you have to reverse the voltage, which makes impossible to mesh such HVDC. And voltage source converters, of course, the voltage keep the same, and you can reverse just only the currents. Then you can put another third part, and so on and so on. Technologies of components. Okay. You know, the most modern, we have an example with interconnect INELF between France and Spain, which is not, I think, driven by technological necessity, but driven by ecological concerns. People are against building new lines, overhead lines. Then the politicians decided, okay, we can go through the mountain by cables, but the length and the quantity of energy it was not possible to use AC cables. Then DC is imposed. By imposing DC, we impose the solution of MMC converters. But here, the first HVDC project with Mercury Halve in 1945, and the last. Really, this is old, very old technologies. The last in operation, and it was decommissioned in 2012. Just to say that the history of a grid is like a mammoth, a very big animal with a big inertia and very long life. Then the solutions we are today trying to put on the field will exist maybe for 50 years. Maybe more in the future. Then we have to think a lot about what could be the solutions. Okay, this is just a picture to say that the technologies, actual technologies are more IGBTs, insulated bipolar transistors, and this technology, I think, is going to be the technology. The converters, the MMC, modular model is the actual which is the Swiss Army knife. In French, we say couteau suisse. It means a tool for everything. This tool for everything can do everything. Manage reactive power from the IC side. You can build DC-DC converters with that structure. You have inside a lot of embedded energy. You can just small calculation with INELF project. Inside each submodel, you have capacitors. By adding all the energy inside the submodels of this converter, you can provide 108 megawatts during 100 milliseconds, which could be sufficient to face many small problems like huge, I think, events in short time. You can add more energy inside, then you can use it as a storage system to face change of frequency or imbalance between energies. Okay, conclusions. I have just 1 minute. Conclusion, operation and communication with Luxembourg research opportunity. Okay, this is very interesting area. It's like inventaire à la Prévert. Prévert is a French poet. He has put in the same basket many words, and the words are playing with us. They can play together. You can use the system to improve ancillary services and increase stability and so on. And to think what could be the future HVDC grid. But we have many things to accept. the HVDC is not only undersea cables or underground cables or subsea cables, it's also overhead lines. They must be acceptable. Heavy investments and many actors, and so on and so on. And we have not any standard stabilized today. And we have, of course, conservatism. We cannot play with the transmission grid like we are playing with the electric car. The consequence could be very dramatic. Okay, what are the locks? At DC interaction, there are many studies about the interaction between DC-AC grids. This loss of inertia, how to improve it, how to reduce the losses, because you are adding more power electronics, then we add losses in the system. The interoperability between devices with old system, new system, and the technologies with breakers, cable, and so on and so on. DC cable are very complicated thing. Okay, measurements and so on. Of course, I think I finished. I'm ready for question, and thank you for listening.
Thank you, Professor Basha. So we have 1 moment for a quick question, which we have received from the audience. So when do you think or you see the first international high voltage direct current network to be in operation in Europe?
Yes, in Europe, now we have the premise, the first path, okay? We have the first HVDC grid is existing since, I think, more than 70 years ago, okay? With Holland, linking between Holland Island, I think, Gotland Island in Sweden with the mainland in Sweden. But if you are discussing about a meshed grid today, there is a point-to-point links. And one of the major projects now is in Germany to replace the AC overhead lines by DC overhead lines from the north to the south. But there is also many studies to connect this point-to-point HVDC grid by DC-DC conversion. For instance, the 2 links from Norway to Denmark and another one to Holland, I think. There is projects to mesh them in order to increase, I think, the reliability of such system, because the point-to-point, if you are lose line, you are losing everything, okay? But by meshing this by DC-DC converters, now it's the first step. The next step could be the real meshed one for hosting the huge quantity of wind energy we have in North Sea in Europe. In China, it's the case now. We have just 2 examples of meshed grid DC grids, but in Europe, 0 today. But in the close future, you have just small connection to I think just to enhance the capacities of exchanges. But in the future, it depends on many things. It depends on the economy. If you have investments, enough money for that. If the second problem, if the technologies, I think we have a collapse of a huge change of technology by silicon carbide converters, then it will make the MMC smaller, cheaper, and more reliable. Thank you.
Thank you. Thank you. Unfortunately, this concludes the presentation, as we have no more time for further questions. But thank you again for your contribution to this conference.
Thank you, Aditi.
So the Energy Game Changers 2020 is done with the presentations for today. Hopefully they have initiated your thought processes, given you lots of ideas. We're now taking a break. So grab a cup of coffee, perhaps make a sandwich, stretch maybe, and I invite you to be back here in 15 minutes when the Energy Game Changers conference continues.